Perfect. Okay, welcome everyone to this event of Lean Agile Delivery and Coaching Network and Digital Transformation in London. Today, we are going to touch a very, let me say, new topic for me at least, but it's a very brand new technology, even if we were just talking about the fact that actually this is more than 10 years old. So we learn something every day. Just a few words about the next event. This is the first event in April. We are going to host a second event at the end of April, 26, for your information, on a completely different topic that is about creating a new facilitation event, and in particular games. And we are hosting Terry, that is a friend that we worked together to develop a couple of games, serious games I'm talking about. So it will be a very interactive event in the essence, because serious games is in the essence very interactive. However, today we have with us Ivan Despot. I hope that I pronounced the name in the right way.
Completely.
From Croatia, so really nice to have people connected in our community outside England. We have some guests also from US here, so really love it. And he is a developer, if I correctly understand, even if his mention is a little bit different, he considers himself a developer relation engineer. So really interesting also as a role. So I hope that you will explain this.
Okay.
And is working in Memgraph, that is a Croatian company, I suppose.
Actually UK based, but a big part of the engineering team is here in Croatia, in Zagreb.
Okay, great. Okay, thank you for clarifying this. Actually, I have nothing else to tell, so I will give you the stage, Ivan.
Yeah.
So please.
Thank you very much for the warm introduction. So yes, hi, I'm Ivan. I'm gonna talk about graph-based stream processing today. It's a combination of using graph databases to run graph analytics on streaming data. So data that's being produced in real time from different kinds of data sources, but essentially it can be represented as a graph. How this presentation and demo came to be, me and my colleague, we created a very simple application during the holidays, and then later on kind of wanted to showcase it and to spread awareness about this whole actually kind of new field that's emerging about graph analytics on streaming data. So let's dive right in. This is me, born and living in Croatia. I got my master's in computer science from the Faculty of Electrical Engineering and Computing in Zagreb, a mouthful. I'm currently pursuing a PhD at the same university. And I work as a developer relations engineer at Memgraph, a graph analytics company. So if you never heard about the role, that's completely okay. It's also relatively new. My job is to create demo applications, tutorials, to cover use cases with our technology, and then kind of spread awareness about the whole field and these newly emerging technologies. So I found myself in there, so it is a cool job, and that's why I love doing it. I love to travel, cook, and I definitely watch Netflix too much. Kind of working on that one, but with no success yet. So first, before talking about stream processing with graphs, let's first cover the graph data model and just the basics from the field of graph theory in mathematics. So this is a graph. It consists essentially of three different structures: nodes, relationships, and properties. Nodes, they represent entities from the real world. So, for example, this is a node that represents a person. That's why it has this label, person. And this is a node that represents a city and a location. That's why it has two distinct nodes. These lines between them, they represent relationships. So how entities are connected to each other. This person lives in this city. Why is it called a labeled property graph model? Because the nodes, they have labels, and both nodes and relationships can have properties. So these are key value pairs that tie some other information to the object. So for example, this person has a property with a key name and the value is Harry. So this person is literally named Harry. Then the other property is date of birth. This could be a timestamp property. So this before was a string, and they can be integers, lists, and so on. So like you will find in a normal database, but the core concept is nodes and relationships. So why is this different than a relational database, and where is it utilized? So when you create a relational database, you probably know that you have to define a schema. So you create the outlines of the tables that are going to hold the data. And these tables, at first, they are not connected. So they exist for themselves, most often to reduce redundancy. So, for example, when we want to find the relationship between two tables, the product table and the order table, we need to connect them artificially using joins in SQL. So the data isn't connected at first. We first must use up some computing resources, and then we can get relationships between two entities. In a graph data model, it's different. So all of the entities are connected to each other. They hold the connection they have to the other entity. So for example, order knows that it's connected to location via the relationship ships to. So this can result in better computational time. It can take up less resources while doing traversals throughout the graph, throughout the network, when you need to do a lot of read-write operations with these relationships. So in other terms, things you will use SQL joins for in the relational model. A core difference as well is that the graph model is pretty flexible. It's not strongly defined. It doesn't have a schema. So the whole graph may look like this, for example, customers, locations, orders, suppliers, and products, but no one can stop us from adding any other node with any other label, properties, and so on. So you can extend it, your data model can change, and this is kind of this NoSQL approach where you don't have a rigid defined table. I mean, most use cases do need relational databases, and they are more suited for them. And in most enterprise applications, you will have a defined table schema beforehand. But there are some use cases where graph databases are a more logical choice because of the nature of the domain. So how do you interact with graph databases? One of the most popular query languages is Cypher. You can think of it as SQL, but for graph databases. So it has a lot of the same clauses like delete, set, return. But for example, this match, it's literally the same as select in relational databases. Then you have functions, mathematical ones, parsing ones, and so on. And you can also define custom procedures and implement them in Python, C, C++, and Rust. This is specific for Memgraph, but other databases support other languages as well. For example, Neo4j is a Java-based graph database, and so the custom procedures are also written in Java. This is a typical example of how Cypher differs from SQL. This is essentially the same query. So we are doing product recommendations on the same data model, but the difference is that here in the SQL query, you need to first join the tables using the join operation, and then you can maybe infer something from the data. Here, it's a different scenario. Even though you probably don't know the Cypher query language, maybe you will be able to follow. So we have a customer with the ID customer 1, and this customer bought a product. And then we check all the other customers who have bought the same product and what else they have bought. We find between these products they have bought, the ones that the first customer didn't buy yet, and then we rank them in the order of their frequency, and we can suggest the most frequent ones as a recommendation. So this is a use case for a graph data model and for a graph data analytics approach, when it's kind of easier to get these relationships between entities. So here between a customer and products they bought, and it's much easier to get these relationships and then use them later on in the query. Now, I mentioned graph analytics a few times. So what I'm actually talking about is graph traversals and graph algorithms. Graph traversals means going through the network via the relationships and maybe retrieving these relationships or changing them. So it's about walking through the graph. And graph algorithms, you probably also heard about some of them, for example, breadth first search, depth first search, shortest path between two entities in a network, the Pagerank algorithm implemented by Google, community detection. There are lots of them, and they are suited for the graph data model. And this is kind of the smart thing you do and the way you generate insights from your data. So, for example, if you run the Pagerank algorithm, you find the influence of nodes in the network, and then you know which one is the most influential one and which one is the least influential one. Maybe this seems a bit abstract, so I included a few use cases and a few companies that use it. So Google implemented a Pagerank algorithm to measure the importance of web pages. So if you used Google search, you encountered the Pagerank algorithm. Then Facebook uses community detection to find densely connected clusters of users, and then they can make friendship recommendations based on them, or maybe target them with the same ads. Amazon uses collaborative filtering to create product recommendations, as we have seen in the previous query. I mean, it's a simplified version, but it's kind of the same approach. And Pinterest and Uber Eats are examples of graph-based machine learning, where we use the graph data models to extract additional features from the data set and then enrich our machine learning model to have higher accuracy scores. So this is a specific use case of graphs and graph analytics. So a typical social network where users are connected via relationships of the type friends with. Here we can do link prediction, a graph-based machine learning approach to find potential relationships between entities. So we try to check which two users are most likely to have a relationship between them occur. So then we can also do recommendations based on kind of these results. This is pretty cool visualization of a graph. This is the Facebook network on a black background, and when the relationships glow, you kind of see the outline of the whole world. So Facebook started with this graph analytics approach also at one point, because the data was just modeled this way, and because they were working with trillions of nodes and relationships, the relational approach wasn't really working for everything and for all use cases, especially the ones where you need to generate some insights from the network. And more or less all the other companies went the same way. Google had also a graph of web pages that are connected to each other with hyperlinks linking to each other and so on. Amazon, again, also found, even though the data could be modeled relationally pretty easily, specific reasons to use the graph model, because it's, for example, easier to create recommendations. It's faster to create them with the graph model. Recommendation engines, already mentioned them enough times already. They are pretty popular. For example, this is a movie recommendation network where you can traverse which user rated which movie, and then which movie is maybe connected not only to genres, it could be connected to terms, keywords, and so on. It could be a combination with an NLP model. This is a supply chain management network when we can use graph algorithms to find bottlenecks, to run business risk analysis, to find where the supply chain is the weakest and where the graph will just fall apart, and maybe it will split the whole supply chain. Fraud detection is probably the most used at the moment graph use case, at least to my knowledge. Banks, insurance companies can use the graph data model because it will result in faster traversals. It will be a lot easier to find all of the entities a fraudulent user has interacted with, be it POS devices, be it other users. Community detection, for example, can also be run to find groups of fraudsters, rings that are working together. There are always connections between them, and it's kind of easier to spot them with graph algorithms and graph traversals. So now that I kind of given you a basic introduction into the whole field of graph databases and graph analytics and why and where they are used, now let's talk about graph stream processing, because as you might have mentioned, a lot of these companies, a lot of these use cases include real-time data sources. So for example, users that are browsing through Amazon, they generate data each second, where they clicked, what they saw, how long were they there, and so on. On Google, users are also clicking all the time. Requests are coming in a matter of thousands in a second, and so on. So these are all stream processing use cases, analytics that need to happen instantaneously, near instantaneously. So we have some input data from different sources. Most often in today's data architectures, message brokers are used. So services that kind of gather the data and then can disperse it to other services. Examples include Apache Kafka, RabbitMQ, Redpanda, Apache Pulsar. So these connect as data sources. And then once this data is created, it enters a stream processing engine. So it doesn't have to be a graph stream processing engines. There are other tools for relational data as well. So for example, Apache Flink and Apache Spark. You run analytics algorithms on them. This can be done using, for example, SQL, using a programming language like Python, in our case, Cypher for graphs. And once data is generated, so something is calculated, what can happen is this data could be enriched. So for example, if this was a customer and we just found out something about them, we can add this data to the customer and then save it to a database. Maybe we can send it to our output stream, so another service can use the results instantaneously for something else. Maybe we need to visualize it, so a person can take a look at it and make a decision based on it. So it's just about enriching created data and gathering some information from it, but in real time, because we need it right now. These are just a few formalizations. So stream processing is a type of big data architecture in which the data is analyzed in real time. It is used whenever you need to extract additional information from your data as it's being consumed. Consumed means read as it's being processed. The processing happens asynchronously. The data source and the stream processing work independently without waiting for a response from one another. So this is very important because we don't want any bottlenecks to happen. We don't want this whole pipeline to break. So for example, if a piece of information wasn't analyzed because one error happened in a particular instance for a particular reason, we would rather maybe ignore this then stop producing new data, because that's just out of the question. So this is happening in real time, and there are a lot of things to take care of in this whole data engineering pipeline. Memgraph here is used as a stream processing engine. So as I mentioned, there are lots of different stream processing being done on relational data, and we are kind of doing it on graph data. So it's powered by an in-memory graph database. So what I talked earlier, Memgraph is essentially a graph database that has a connector to real-time streams, and then you can run graph algorithms, dynamic graph algorithms, and graph traversals on real-time data as it's being created and added to the database. And then once it's analyzed, the output can be used later in other applications, visualization tools, or just the newly created data can be enriched and saved. ksqlAlchemy is a library that we used in our demo that I'm going to show you. It's an object graph mapper. If you maybe heard about ksqlAlchemy, which is an object relational mapper, it's just a pumped up driver in Python that also has additional features to make the development process easier. So instead of writing, for example, Cypher queries, you can write Python code. You write Python methods that get translated into the Cypher query language. That's how ksqlAlchemy works as well. So you're trying to use Python objects and steering away from this new language and new constructs. You get objects from the database as classes in Python. So you have a node class and a relationship class, and you interact with them in a manner that you're familiar with. If you want to check it out, I also created a Jupyter notebook that showcases this. library, and it's open source. So if you want to contribute to it or use it for something, you're always welcome to. And now about the architecture of the demo application we created. It consists of 5 essential services. So at the beginning, we have the data source. This has to do with what the application was meant for. So it was holiday season, and we wanted to find the most Christmassy person on Twitter. So we analyzed tweets. I'm going to touch upon the data set in maybe the next slide. So we wanted to analyze the Twitter network, and that's why we scraped Twitter for a few seconds, and it didn't take more than that. And we combined all of this data that we scraped in a CSV file. Why did we do that? Why don't we do it right now in real time? Because we can't be sure that enough tweets are going to be generated with this particular hashtag. The hashtag we used was Christmas. So our CSV file contains around, I think, 2,000 entities, 2,000 retweets that included this hashtag. So we wrote a simple Python script that's going over the CSV file, and it's generating messages each second. So we are just simulating a connection to the Twitter API. Now these messages are being streamed to Kafka, a Kafka server on a specific topic. What this means is that our other services can listen on this topic and consume the messages. So whenever they are created, they are available to the other services. And one of these services is Memgraph. Memgraph ingests each tweet as it's being created. It creates a node for it. It creates a relationship, who retweeted whom. And some graph algorithms are being run, PageRank and community detection. I'm also going to talk about it later. So once the results are calculated, they are being sent again to another Kafka topic. So the backend server written in Flask using Python can consume these results. So now we have the PageRank value and the community detection result, and we can send it to the front-end client so it can be visualized. And I'm going to show you that. So this is pretty basic architecture. It was the simplest one we could come up with that kind of takes care of all the stream processing needs we had for it. So now it's demo time. I'm just going to show you the data model before I power up the application. It's one of the simplest ones. We only have nodes with the label user. So a lot of Twitter users, each of them has only one property, it's username, and it's a unique one, so Twitter username. And all of these users are connected with one kind of relationship, retweeted. So we scrape Twitter for users who were retweeting each other, and these tweets contained the hashtag Christmas. Why? We wanted to find the most Christmassy person at that point. It was the most popular topic, and we didn't want to do COVID. Which algorithms did we run to find the most Christmassy person? We ran the dynamic Pagerank algorithm. So we wanted to find the influence of nodes in the network. And the one with the largest PageRank value will be the most influential one. And we wanted to do community detection just to see if a community will also form around this most influential node. Because we think there could be a correlation between these two. And why does it say dynamic? These algorithms aren't traditional PageRank and community detection algorithms. They are not being run on the whole data set. So for example, if you had a million nodes and a million edges and new ones are coming in and you run the PageRank algorithm on the whole network, it will take a few seconds, well, maybe a few minutes. It's too much for stream processing because data is being created each second in vast quantities. So we need to perform dynamic algorithms. These only take into account the context around the specific node that was created. So for example, the nearest neighbors, and it only takes into account those that need a recalculated PageRank value. So it's not going to go over the whole network. It's not recalculate the PageRank value for each node. It's only going to recalculate the value for the nodes that are going to be affected with a newly created node. That means dynamic. There are a lot of other dynamic algorithms outside of the graph sphere. And we also implemented a dynamic version of the community detection algorithm, a propagation one. It also, whenever a new node is added, it tries to find the cluster to which it belongs to, and it only tries to adjust the cluster information of the neighboring nodes that are affected by it. So I'm gonna power up the demo application. Bear with me, it's gonna take me a minute, probably. I'm using Docker for it, an orchestration tool. If you never used it, it's pretty cool. It's now gonna start a container that has Apache Kafka, the message broker, a container with a Python script that's gonna go create the tweets every second, a container that's gonna run Memgraph, a container with a backend server in Flask, and so on. So it kind of takes care of this whole process instead of me. And now that all of these backend services have started successfully, I also fired up the front-end client, which is a React application. And most notably, it's a very simple one, but it uses the D3JS JavaScript library. It's a great visualization tool. I think it's also open source. Whenever we have a need to visualize a graph to create something custom, we kind of just go with D3JS because it's pretty cool and has a lot of options. So the client is running on localhost 3000. And let's see if the data is gonna start being produced and start being analyzed. There's always an option of the demo not working in a live setting. I'm used to that. So here, as you can see, new users are being added, and these edges between them mean they have retweeted each other. As you can probably guess, the smaller ones have retweeted the larger ones, which means that the PageRank value of the was calculated. This larger node, it has a larger PageRank value, and the radius is directly proportional to it. That's how we created it. So we can just visually see which user is the most influential one. So the largest one currently is World Music Award, and it was the largest Twitter account that tweeted at that time. It had like 100,000 followers, which was a lot more than all the others. So this is the Pagerank algorithm. As you can see as well, the radius is changing. That's because when new nodes are created and relationships are added, the PageRank value for some of them is recalculated because of the dynamic algorithm, and some may lose on influence and some may gain on influence. And then we use a WebSocket connection between the backend server and the front-end client to always send this new information and to update this visualization. This is the community detection algorithm. It colors the nodes based on the community they belong to. It's a propagation algorithm, so the more nodes get added, the better the results will be and the better the communities will propagate through the network. I'm gonna show you the data. So this is a Memgraph Lab, an application we use to interact with the graph database and write Cypher queries. As you can see, this is the number of nodes and the number of relationships in the database, and it's increasing every few seconds because new data is being ingested in Memgraph and being analyzed. And for example, the graph schema, it's this. So user and a lot of users which have retweeted each other, and that's more or less it. Yeah, and these ones are also getting bigger, and the World Music Award is definitely coming out on top. So how did we create this? What's in the backend? What's actually happening? How much did we code? Well, beside the basic functionalities of the backend server and the front-end client and so on, the trickiest part is actually connecting the services and running these analytics. So what did it take to create them? So first, what we needed a transformation module. It's something that tells the stream processing engine, in this case Memgraph, how to interpret the messages that are being created. So this is a message that comes in each second. So a source username and a target username in JSON format. So which user retweeted the other user. And then we say, okay, use this Cypher query to create a node and a relationship in the database. So create a user node with this username, source username, create a endpoint node user with this target username, and then connect them with a relationship retweeted. And that's it. Now, when messages are created, when new retweets are coming in, the Graph database knows how to store them. Okay, now the data is stored, it's in there. What to do? We set up a Pagerank algorithm, the dynamic one, which means we only executed this default query for creating the PageRank trigger. So it says each time a new node or relationship gets created, run the PageRank algorithm on them. And once it's finished, then you have the rank, then create a property on that node and assign it this newly created rank. So when a new user comes in, it only has the property username, but once the PageRank value and the community detection values are calculated, they get added as new properties to the node. And then once the node is enriched and it has these values, it's sent to another Kafka topic. So the backend server can also have this info. So the front-end client can visualize it. So at the end, we created and started the stream. So we connected Memgraph to this Kafka topic. We told it, hey, the topic you are listening to is retweets. What you are doing with the new messages, the JSON messages that are arriving, is written in the transformation module twitter.tweet. It's the one from the first step. So do this on every new message. And this is where the Kafka server is located at. And then create stream, start stream. This is written with a GQLAlchemy Python library. So the one we use to interact with the Graph database, an advanced driver. And at the end, we created another trigger that's going to be activated each time a new node and relationship are created. We want to send them again to a Kafka topic so they can be picked up at the backend server and the front-end client, because we want to visualize the nodes and the relationships there. So we send info about them, their ID, and so on. And it happens each time something is created. And essentially, when it says here, call publisher.create with created objects, publisher.create is a Python script, so a custom procedure we've written. In Python, it has like 20 lines, and it's just a Kafka producer, which sends this node or relationship to a Kafka topic. So we kind of use these custom procedures with which we can extend the Cypher query language to create something that we needed at that moment, a way of transporting data to a Kafka topic from the database directly. And this is the summary. Create a transformation module in Python so that the data can get into the database. Run the PageRank and community detection algorithms with GQLAlchemy, so you get the results you want. Create a stream and start a stream in GQLAlchemy, which means start ingesting the data in the database and start running everything you set up before, so PageRank and community detection, and create a trigger and a module to send all of the results back to another Kafka topic, so it can be picked up by the other services, in this case, the backend server and the front-end client. So this is kind of all of the connections in the architecture diagram, except, for example, if I missed something. So here, the connection between the backend server and the front-end client is a WebSocket connection. So each time the Kafka consumer in the backend picks up on a newly created node or a newly created relationship with their PageRank and community detection values, it sends it to the front-end client via WebSocket, so it can be visualized in real time. The app, once we created the demo, we kind of didn't think about scaling. It was only supposed to run for a few minutes. So this is why it looks a bit funny at this moment with more nodes. But as you can see in the few seconds that we ran the Twitter scraper and scraped the data, This was definitely the most influential account, and it kind of took over the whole network. And as you can see, it's kind of doing the same thing in the community detection algorithm. The community may not be very large, but it's the largest one by far. It's these blue ones with World Music Awards at the center. Why it's behaving this strange way? Because we created forces between the nodes just for visualization purposes. And then when you drag them around, they kind of act with a force on each other. Pretty cool, a feature of D3.js. My colleague worked on that most, but I think I can also answer a few questions if you have them. And that's it. These were the results. It took us a couple of days. It wasn't really that hard because we didn't implement any of the algorithms ourselves. We didn't implement the Pagerank algorithm, and we didn't implement the community detection algorithm. We just used them with the graph database. So that was easy, but the hardest part by far, connecting all of these services into a relatively stable pipeline that generates data, analyzes it, enriches it, saves it, and visualizes it. So a lot of moving parts which you need to fine-tune to work with each other. If you want to take a look at the data set, we imported it into an online sandbox. So you can just run Cypher queries if you want to know how the language functions. So here we just call the Pagerank algorithm the traditional one, so not a dynamic Pagerank algorithm. On the whole network, we get a PageRank value for each user, and then we return all of the calculated PageRank values with the users, and here they are ordered in descending form. So World Music Award, definitely, even by traditional PageRank standards, is the most influential node in the whole networks by far. And you can also use this to visualize the data as well. So this is all of the users who have retweeted the user World Music Award, and all of them are visualized with World Music Award in the middle. So you can also try out other Cypher queries, other graph algorithms, and so on. This is a standard network. And thank you for your attention. I hope I didn't bore you to death. Please, if you have any feedback, if you think I didn't describe something was out of the ordinary, just shout. I can handle criticism. Corrado, you're muted if you're trying to.
Yeah, I'm still alive, even if on mute, but still alive. So thank you for sharing this. There are some guys that actually entered just in the last minute, but fine for that. Any question from the audience?
They will at least have the YouTube recording.
Yeah, absolutely. Actually, I have a question, Ivan. In a standard enterprise application, for example, you mentioned the bank environment, okay, where you can, when you want to track frauds and what else, how long it takes to implement an analysis tools using this technology? I can understand this is a pretty generic question, but given your experience.
Yeah, I mean, we were in similar situations. So for a bank, it takes a lot of time. So this is probably a very specific case where you kind of have to go through a lot of regulatory procedures, kind of things you have to, requirements you need to fill out before you can even interact with a mock data set the bank is using. And then you can just start modeling the data set and creating a graph model that's going to be efficient, that's going to be sustainable, scalable later on. A lot of time goes into that, and you are not even interacting with real data because, of course, they can share it with you. They need to come up with mock data. So
yeah.
banks
So
are pretty specific.
Yeah, so the model that you are creating is really based on how the data are configured, let me say, in the backend. This is true for every application, I suppose, not just for bank.
Of course, and I mean, the same goes for relational databases. They also need to model the data in a logical way.
Yeah,
here, you maybe need to put also a bit of thought into it, because even though the model is flexible and you can change it later on, this could deal you with more problems if you didn't approach it the right way. Maybe something should have been a property on a node and not a specific node for itself. So there are benefits and disadvantages to either approach, and you think about it before you kind of go the production route.
Thank you. We have a question from Steven. Please, Steven, unmute and make your question directly to Ivan.
I think you are maybe muted.
Yeah, we cannot hear you. Okay.
So I caught
the microphone.
Yeah, it's the microphone, not the system. Yeah. So that's that. Hiya. Hi. I've got an application that I could think of using this for, and it's kind of part of. It would be more based on text files. So when I go to one of these meetups, one of Corrado's meetups, I write up notes of what I've learned, and then I cross-reference it. And I think
that's
having
a great
those,
approach.
So having cross-referencing and some way of visualizing that data. So I'm assuming if I had that data in a structured way, I could say Corrado's 12th of April thing introduced graphing, and then I've seen that somewhere else, and it begins to link up, and those tags link. I assume you could do that using this, and you just have to have a common folder.
Of course, I mean, you could. It's a graph in essence, and you could just create nodes that represent different topics and nodes that represent different meetup events, and then connect them maybe even with nodes that represent speakers or the talk or the technology in question. And yeah, I mean, it's a graph model. It's definitely one that sounds interesting.
Yeah, I think it was also in a book called How to Take Notes, or something like that, by some professor who wrote like thousands, the most papers ever, and that's what
did you say it was called? How
to Take Better Notes, or something like that.
I definitely need that book.
Okay, Ivan, you have the killer application.
Anyway, so yeah, I'm just thinking practicality. So thanks for that.
Thanks for the question, Steven.
Yeah, thank you.
In the meantime, while you are thinking for another question to Ivan, in the chat, I put some references to the YouTube channel, to our LinkedIn group, and also I put the link to the next event. So if you want to take your seat at the end of April in our next event. Okay, good. Any more questions for Ivan? Yeah, thank you for showing.
I'm gonna take that as a compliment that everything was clear, hopefully.
Well, actually, for me, it was really, really technical. So I miss sometimes in the, let me say, technical details, in the technology details.
Yeah, I never know how much to go into the basics, the theory behind it. Then it will take up more than an hour.
Pardon me. Just a quick question for me. I see that you run your demo on a Windows machine, correct?
Yes, I am a proud Windows user because since they introduced VSL, it kind of eliminates my need to have a dual boot system with Ubuntu. So I can just open here a nice containerized version of Ubuntu, and I can do everything in Linux.
Sorry, what is this technology? I'm curious.
VSL, Windows Subsystem for Linux. So it's kind of Linux on Ubuntu container is running in the background, and I can interact with it. So I'm currently in this terminal on a different Linux account, but it also connected to my Windows host. So I'm currently in a Windows directory, but I am using a Linux terminal, so I can install everything like in Linux.
Windows Subsystem
for Linux. I'm not really into the technical background of this. Not really sure if I'm correctly using the nomenclature, but it's pretty cool.
And this is just for the terminal, not for the UI in Linux, correct?
Yes, I think there are some options even to run visual applications, but I never had a need. I only need the terminal.
Yeah,
for
sure.
coding.
It makes sense because you need the server for them.
Yeah.
Okay, really interesting. In the meantime, Steven put in the chat the exact reference to the document, to the book that you mentioned.
Nice, really, thank you. My notes are currently everywhere, on paper, in physical format, on Google Keep, in Gmail draft email messages.
And on a Moleskine,
Nice.
Okay. Nice. Thank you very much, Ivan, for this presentation. I found really hard, but I really enjoy because I learned something that I didn't know. So for me, it was really, really helpful. And I think that also for the other attendees. So I don't think we have more questions. So thank you again for sharing this with us. I will let you know when the video of the session will be available on YouTube so you can review it. Okay?
Oh, thank you.
Thank you all for being there.
Bye.